In this video, we are going to look at functions of two variables and figure out where they are differentiable. Then we'll explore the connections between differentiability, continuity, and partial derivatives. Let's begin with defining differentiability for a function of several variables. A function f is differentiable at point P, say x0, y0, if f of xy equals f of x0, y0 plus the partial derivative of f with respect to x evaluated at x0, y0 times the quantity x minus x0 plus the partial derivative of f with respect to y evaluated at x0, y0 times the quantity y minus y0 plus e of xy for all points xy in a delta disk around P. And the limit as xy tends to x0, y0 of the error term e of xy over the square root of the sum of the quantity x minus x0 squared and the quantity y minus y0 squared is 0. Another way to think about the error term is as a measure of to how closely the tangent plane comes to the surface defined by f of xy in a small neighborhood of P. Let's look at a theorem that relates differentiability and continuity. If a function f of xy is differentiable at a point x0, y0 in its domain, then the function is continuous at x0, y0. We have seen this result before with functions of a single variable. And just like with those functions, this implication only goes one way. Just because a function is continuous at a point doesn't mean that it is differentiable at that point. Our next theorem does relate the continuity and differentiability, but it has some restrictions on it. For any function f of x and y, if the point x0, y0 is in its domain, the function and its partial derivatives exist near the point and are all continuous at x0, y0, then the function is differentiable at x0, y0. Let's look at a function and show that it is differentiable at a specific point. In order to show that a function is differentiable at a point, it needs to satisfy this equation when x0 is 1 and y0 is 0. We need to find f of 1, 0, and evaluate the partial derivatives of the function with respect to x and y at 1, 0. Let's find f of 1, 0 first. Substituting 1 for x and 0 for y gives us 3 times the quantity 1 squared plus 5 times 1 minus sine 0. This is equal to 3 plus 5 minus 0, which is 8. Taking the derivative of f with respect to x gives 6x plus 5. Evaluating fx at 1, 0 gives 6 times 1 plus 5, or 11. The only term in f that contains y is the sine term, so the derivative with respect to y is negative cosine y. We know that the cosine of 0 is 1, so fy of 1, 0 is negative 1. Our next step in checking that f is differentiable at 1, 0 is to substitute the values we found at 1, 0 into the function and solve for e of xy. After substituting, we find that f of xy is 11x minus y minus 3 plus e of xy. Solving for e of xy just requires subtracting everything but e from both sides and then switching sides of the equation. Now that we have e in terms of xy and f, we can replace f with 3x squared plus 5x minus sine y and have e in terms of x and y. Our substitution gives us 3x squared plus 5x minus sine y minus 11x plus y plus 3. Upon simplification, we find that e of xy is equal to 3x squared minus 6x plus y minus sine y plus 3. We now want to substitute this for e in the limit and verify that this is equal to 0. Our last steps in showing that f is differentiable is showing that the limit as xy approaches 1, 0 of the quantity 3x squared minus 6x plus y minus sine y plus 3 all over the square root of the quantity x minus 1 squared plus the quantity y minus 0 squared is 0. Now we want to evaluate the limit. Notice that it has been simplified slightly to save space. We want to multiply the limit by the limit as xy goes to 0, 1 of the quantity x minus 1 squared plus y squared, so we can eliminate the denominator. Once we simplify the fraction, we have the limit as xy approaches 1, 0 of the quantity 3x squared minus 6x plus y minus sine y plus 3 times the square root of the quantity x minus 1 squared plus the quantity y minus 0 squared. Looking at this limit, we see that this term goes to 0 as xy goes to 1, 0. By the product property of limits, this means that the entire limit goes to 0. Therefore, f of xy is continuous at the point 1, 0.